So what is the example? The example is, let us take the set which consists of two elements, E and A, and which has a multiplication table. So this is a multiplication table. So this is a EA. So E times E is E. E times A is A. A times E is A. A times A is E. Okay, so this is a group. Okay, so now notice that A times E is E times A. And so that means that this is, of course, it's trivially abelian, right? It's an abelian group. Now, what is the inverse of A? What is this?
E.
A.
A. So the inverse of A is itself, which is the comment I made before, right? That because A times A is E. Okay. So often this group is called Z2, because if I take the set 1 and minus 1, where these are the numbers, 1 and minus 1, then under multiplication, we get 1 times 1 is 1, 1 times minus 1 is minus 1, minus 1 times 1 is 1, minus 1 times minus 1 is 1. So we see that, G as defined above.
So the third one should be minus 1, I think.
Yeah.
So as defined above is isomorphic to Z2, right? So because of that, this group is often called Z2. And this is a case of a representation. This is an example of a representation. Of the group Z2. So there are other representations. So for example, you can say, okay, this is kind of you can always, I challenge you to find two matrices, M1 and M2, which are not numbers, which also follow the same multiplication table. Okay, so try that. That would be another representation. Okay. So I want to give you some exercises now for you to do at home and submit when the link is available. So I'm going to, these exercises, I'm going to highlight them with blue and border them with red so that you know clearly that those are the ones you have to do. And then we'll take a little break. Right. So, show that if G inverse is the right inverse of G, that is G inverse is E, then it is also the left inverse. Then it is also the left inverse. So G inverse of G is then, okay, show this. So that's number one. Number two is show that if E is the right identity, then it is also left identity. And number three is that, show that the inverse is unique. That is, suppose you have, say, G1 inverse is E, and G2 inverse is E, then that means that G1 inverse is equal to G2 inverse, okay? So these are some of the exercises I would like you to do. Sorry, it's not very pretty, the box, but will do. Okay, so do you have any questions? Okay, so if not, let's carry on. How many people do we have? We have 25. Including 2 of them. Okay. So next, let's define the subgroup. So what is a subgroup? So sometimes we write this, let G be a group if H is a subset of G such that H itself is a group under the same multiplication then H is a subgroup. Okay. So we should define along with this what is a proper subgroup. And it's kind of very, very obvious. Suppose that if the whole group G itself is a subgroup, trivially, and the identity element itself is also subgroup trivially, so these are not interesting, and they're called improper subgroups. So these are improper subgroups. So if H is a subset of G, but H is not G itself, or H is not just the identity element, then H is a proper subgroup. Okay. Okay. I think we have time for a couple of 1 or 2 examples. It's very important to have examples in this business. Otherwise, you just lose track of whatever abstract stuff that I'm saying. Number one, the real numbers under addition. This is a group. So for example, if A is an element, what is the inverse of A?
Minus
Right. So that means that O is 0 is
identity.
Yeah, identity element.
identity. Very good. Okay, and of course, all the other things are, we know that real number addition is associative. So is this an commutative group, or is it an abelian group or non-abelian group?
Abelian.
Abelian group.
Yeah.
Right, so, okay, so that was easy. What about the set of integers under the addition? Is that a group?
No.
No, it's not associative.
It's not associative. 1 plus 2 plus 3 is not equals to 1 plus 2 plus 3.
Oh, sorry, I heard division.
Oh, this is plus, sorry, yeah. Addition. Okay, so it is associative, right? So it is a group, but is it a subgroup of something?
Real numbers.
Yes. Of this guy, right? Yeah. Very good. And what about the real numbers under multiplication? Is that a group?
No, sir.
No, why?
Zero has no multiple.
Zero doesn't have an inverse.
Right, exactly. So what if I said R minus 0? Is that a group?
Yes, sir.
Yeah, it is.
So this is a group, this is not. Okay, so it's 5:58. Maybe we can take a little break and come back here at 6:10. Is that okay?